linear relationship. What if I do something like this? If I have a graph that looks like that? It's part of a quadratic, absolutely. You may want to flip back actually even to 1.4 is where these actual terms are. They were in your study guide as well, as we talked about. So there we go on page 21. You can see these are nonlinear relationships. So this would be a quadratic relationship. And the key here is that it's a squared relationship, right? So if I step on the gas in my car, right? Are you comfortable I have no velocity to start with, pretending I'm stopped at a stoplight, right? And Alex is there revving his engine in his Jeep ready to race us, right? And we step on the gas, because my minivan will, of course, beat his Jeep any day, right? No, he'd probably kill me, right? My velocity curve, if this was a velocity over time, velocity is going to increase exponentially. Why? Because we're accelerating. Our velocity is increasing over time. Does that make sense? So it wouldn't be a nice straight line, right? This would be like how your grandmother maybe would increase her velocity, right? Very slow, very steady, right? Whereas this is a much quicker, right? So that's quadratic. How about this here? You can flip over one page here if you want to look on page 22. They call it an inverse relationship. Meaning if one goes up, the other goes down. Right? Does that make sense? And again, not a linear relationship. There's not an even piece between them. The further along I go, the lower it gets. Right? Starting very high, slow. So this would be I'm stepping on the brakes. Right? And I'm decelerating. I'm slowing down. I have a negative acceleration. Right? So my slope is negative on my graph. And I'm coming not quite to a stop. I didn't get all the way to 0, but I'm slowing down significantly. Makes sense. And again, those are the terms you wanted to know from 4.1. Again, these are on your study guide. We talked about how to interpret graphs yesterday. We went through all the different pieces of what it meant to be moving different directions. Any questions as far as that goes? We're cool? Okay, so 2.1, we started talking about new ways of representing motion. And don't laugh at my terrible drawings. Well, I used the shapes. Yeah, I used the shapes. Actually, I drew one of them with the shapes and then I copied it. So, here we have a car that's driving, right? We probably should have given it some sort of a background, right? Let's pretend it's the nighttime. Oh, that's a terrible star. And here's the moon, right? Good? Okay? So it's moving down the road. Are you with me? It's moving in this direction. And what we've done is we've taken a snapshot of this car, right? Over and over again at intervals of time. The same interval of time. You can say 1 second. How about that? It can be whatever you want it to be. And we've put those all in one image. Does that make sense? What do we call this? There's a name in physics for this kind of something. Yes, sir? A motion diagram. Okay? This is basically, again, remember we're representing motion, right? I can't actually go out on the road and look at this car. We're just giving ourselves a picture so we can see what's happening to it. Okay? The key point is that each of these cars are representing the same amount of time. Does that make sense? That's a key point with motion diagrams, is it's the same amount of time. So if each of these are the same amount of time, what can you tell me about the distances between them? They're the same in this picture, right? At least I tried awfully hard to make them the same. So then what can you tell me about this car's velocity? It's the same throughout the whole thing, right? It doesn't change. Are we cool? What can you tell me about its acceleration? It's not. It's 0, right? It's not speeding up or slowing down. Does that make sense? Are you comfortable that most people can't draw very well? At least I can't. So therefore, instead of cars, how about we just use dots? Does that make sense? We'll say here's one point that represents this something, whether it's a car or a person or a bird or whatever. Is that cool? And we can then even get rid of the cars so we just have dots. Are you comfortable? This is the same motion, right? Notice same, the same. They're still equal distance apart, right? What do we call this in physics? And again, there's a word for it, a term for it. Keep flipping past motion diagrams. You read this all last night, right? A particle model. This is our particle model, right? Again, same motion as this, right? No difference, no change. But instead of having cars, we just simply put dots. Are you with me? What if, instead of them being like this, what if and let's just get rid of that guy. What if instead your particle model looked like this? Because remember, each of these dots represent the same amount of time, right? It's accelerating. Does that make sense? It's getting faster. It's moving quicker. And you know that because, and they're not quite even, I apologize, but these are close together, right? So the distance it's traveled increases each time. So it has to be accelerating. Does that make sense? So you will definitely see these in the future in this class. Rarely do we use motion diagrams because really, we can't draw, right? At least I can't. So, but you will definitely see particle models in your future. Okay? But are you comfortable that dots sometimes don't carry as much information as we want? Like, we can make an assumption about what direction this thing is going, but are you comfortable it could be going the other way too? But does it give us a whole lot of information, right? So therefore, how about instead of dots, we use arrows? And instead, we have a name for those arrows. Anybody know what we call those arrows? Again, physics has their own terms for everything, right? These are called vectors, right? And the key about a vector is the length matters. So the longer the arrow, the more of whatever it's measuring or whatever it's representing you have. But still, well, it's not necessarily tied into time. If I'm putting them like this, yes. Each of those would be, let's say, 1 second worth of time. I would agree. But you can also just have a vector that stands alone by itself to represent a certain amount of velocity or a certain amount of acceleration or a certain distance. Good question. So again, this would represent, hey, if these are distance vectors or displacement vectors, yeah, you're going that amount of distance in each one of those time frames, each one of those seconds. Does that make sense? All the same motion, right? We're still talking about the car going down the road, right? But now we've just got 3 different ways for us to represent them. Motion diagrams, particle models, and vectors. And the 4th one we already talked about, that was graphs. We could graph this motion, right? And so now I've got 4 different ways of displaying motion without actually having to go watch a car move. Does that make sense? All right. The one last thing about these vectors is that they can have direction. They can give me information about direction. Okay? So if we were to say that these are 2 people running, you comfortable to say this is representing 2 people running? Okay? And this arrow is representing Lucas running. And this arrow is representing Jason running. What can you tell me about their runningness? Give me some hands. What do you think? I want you to think about it. Got 2 hands. What can you tell me? 3? What can you tell me about this motion based upon just these arrows? Lucas, give me one thing.
I'm spending a lot more time in motion than Jason is.
Okay. You said they're just spending more time in motion? Okay. If we were to say they were time vectors, I would agree with that. What if I say they were velocity vectors? So these are showing us speed. Are you with me? These are showing speed.
They're going the same speed?
Okay. What made you say that?
Because they look the same size.
What do you mean as far as length goes? Okay. And, okay. What do you think, Matt? Okay, so if these are velocity vectors, Lucas is going faster than Jason is. Are you comfortable with that? And how do I know that? The length. Okay? So don't get, again, I don't want you to get confused with the time piece. If we're putting a whole series of these together, then we're saying, okay, these are all the same time frame. But if I'm just looking at them individually like this, they're representing just the velocity in this case. That's what we've chosen to do. We could also go distance and say that you've covered a longer distance than Jason did. Again, vectors can be used for almost anything. But we'll call them velocity vectors. Nick, what else do you see? Yeah. Absolutely. And you know that because this is facing this direction and this one is facing the opposite way. Does that make sense? So two big key pieces we can get from this is that number one, Lucas on the bottom is going faster, right? Jason's going slower. And they're going in different directions. Another thing you want to add? No, those are the two pieces you got? Okay, question.
I was just going to ask if Jason was slowing down.
Awesome. So because we're saying these are velocity vectors, it doesn't mean he's slowing down. Because velocity is simply telling me, are you comfortable I could measure this and we could say that this length represents 10 meters per second? And let's say this is about half of that, maybe a little less than that, maybe it's a fourth. So this would be 4 meters per second. In other words, they're proportional, right? If I were to take and put two of these here, there should still be a little bit left over. So does that make sense? You could actually use a ruler and measure and like say, okay, yeah, that's 10, that's 4, okay. This is the proportions to it. It has a scale. Does that make sense? Question?
They're both under 1 second.
If we're saying that this is just an amount of time, I agree with you. I hear you. Sir? It's a good question. No. They don't change the thickness to represent anything. They will change the length, though. It's a great question. Wouldn't matter. But again, the length does. So we'll do some drawing of vectors and understand, Eric, I'm not going to like pull out a ruler and make sure you've got it exact, but there should be an obvious difference between your lines if they're of different speeds or distances. Does that make sense? But again, we're not, now if you were going to be an architect, that would make a difference, right? You would have to make sure your scale is exact, because if you drew that blueprint wrong, you would have a building that would fall down. Does this make sense? Any questions here? Anything else? So we got, these are velocity vectors, right? The arrow side makes a difference. Tells us what direction we're going. We don't know what direction this is. We just know they're going opposite directions, right? You could be going north and they could be going south, be going east and west, could be northeast and southwest. We don't know. We're not given that information, but we know they're opposites. One last thing here. Are you comfortable that I could actually take these and bring them and do something that we call vector addition? In other words, like I said, these represent amounts, right? So let's keep the same amounts. We said this was 10 meters per second, and this was 4 meters per second, right? So let's just take Lucas in this case. If Lucas ran at 10 meters per second, then stopped, and then ran at 4 meters per second the other way. Or perhaps somebody else is pushing on him at 4 meters per second the other way. That's actually probably the better way this would work. What would be the actual resultant? In other words, the leftover piece. What would his actual motion be? Are you comfortable that it would be 10 minus 4? Which would give me 6. So I can actually use them like numbers, these vector pieces, to represent motion. And we'll do oodles of these kind of things. We'll actually even use sine, cosine, and tangent and put two different vectors together, one going this way and one going this way, and we'll find this resultant and find the, we'll do all that stuff in the future. Not yet, not yet. Okay, yes, sir. No, they would give you the numbers. That's a great question. They would definitely give you those numbers. Sir?
Why do they call it addition?
Because you're adding a negative. Does that make sense? I hear you completely. I hear you. This is a 10 centimeter, right? In the positive direction, we're calling to the right positive. And this is a 4 centimeter, but it's in the negative direction. So we'd actually call it negative 4 because they're going oppositely. Remember, it doesn't matter which way is positive. It's up to you, Nick, to determine. It's up to you to figure out which one it is. Yes, sir? Yeah, no, it's excellent. So you're seeing this new convention in physics, right? It's a little bit different than mathematics. Negative only is telling me about direction. That's all it's telling me. Does that make sense? And if you determine that, we call that a coordinate system. If you say the right is positive and the left is negative, so be it for the problems that you're dealing with. When you're given a problem in a textbook, they'll give you some information. If they don't, usually we assume right positive, left negative, but it doesn't matter. We're just prejudiced against left-handed people. You know, that's what it boils down to. Yes, ma'am. Yeah, exactly. Exactly. And so if I wanted to actually write this correct, Michael, which I appreciate you pointing out, it should be 10 plus negative 4 equals 6. Exactly. Exactly. But are you comfortable if I put another arrow down here, right? If I had a third arrow, I could put another arrow on here, and now you'd just be adding more in the same direction. We go what we call tip to tail. So the tip of this guy to the tail of that guy. And because it's going backwards, it gives us a smaller resultant. But if I were to take, let's see if I can do it here. It doesn't matter, to be honest. If I can move, let's see if I can get this to work. No, I thought there was a way that I could flip this. Oh, there we go. If I do this, right? So now how fast is Jason running? 10 plus 4, right? I'm adding those two pieces together. Does that make sense? Yes, ma'am.
Would that just be just as good as one whole line?
Cool. Yep. The whole line we would call a resultant. This is the result of these two things being put together. Absolutely. It means the same thing as the whole line. Sir? I've only been teaching this for a little while. Yeah. So will you very shortly. Very shortly. Monday's our test, right? Yeah. Yeah? Yeah. Unit 1 study guide, right? It's good. Yep. We're a little bit past what we're doing on that study guide. But it just made sense for us to keep going because you all were with me. Questions there? So again, if I pull up that study guide, right? This is what we were just finishing, right? Make sure you understood how to represent the motion. 4 main ways, right? Motion diagrams, where you're actually drawing the pretty pictures. Particle models with the dots. Vectors, where you're drawing the arrows, and those will give you the lengths and the directions matter. They tell you information, right? And then graphing, where we can use to predict things we didn't actually test. We can extend it further than we actually went. Sir? Yeah, understanding the different pieces there. Yeah, yeah, certainly. Are you with me? Any questions there? Cool. 17. All right. So we are going to spend the last half here with you doing your presentations of your physics posters. So give me a moment to pull up our first one. Is going to be Eric Portillo. Come on down. And give me just a moment to pull it up here for you. And again, please don't be distracted by anything else. Give Eric your full and undivided attention as he tells us about his career.
For my presentation, I did an astronomer. Well, studied an astronomer, and